Buenos días a todos. Gracias por asistir a esta sesión del Seminario de Ciencia de Datos. Hoy tenemos el placer de tener entre nosotros a la doctora Ginestra Bianconi. Ella es profesora de Matemáticas Aplicadas en la Escuela de Ciencias Matemáticas de la Queen Mary University of London. Además es miembro del Alan Turing Institute. Y pues el tema de hoy es bastante amplio, aunque no parezca. Nos va a hablar de redes de alto orden y dinámica en las mismas redes. Now I want to switch to English. Ginestra, so you can start at this time. It's yours, the audience, and thank you for accepting the invitation for this seminar. Please.
Thank you so much, Hector. It's a real pleasure to be here with you, and also if, remotely in Mexico City. I've never been there, but I hope that maybe one time I can come. So today I want to speak about higher order networks and dynamics, and this is a recent work that I have been doing in the last 5 years or so, I think. But most of the work I will mention is quite recent. So in network science, there has been a lot of success in characterizing complex systems with networks that are just for nodings, so elements of a complex system and their interaction. But actually, recently it's becoming clear that complex systems include also higher order interactions, so interaction between more than two elements. And these are captured by higher order networks that have that not only formed by node and links representing pairwise interaction, but they are also represented by triangle, tetrahedra, and so on. So there are a number of motivation to study higher order networks. So for instance, in brain data, you might have 3 regions of the brain that are activated, correlated pairwise. And so you have these 3 time series that are pairwise correlated, or you can have the activation at the same time, meaning that this is a 3-body interaction of the 3 regions of the brain simultaneously. In protein interaction network, you have actually that protein form protein complexes, which are formed by more than 2 different types of proteins, and these complexes are the object that performs biological functions, so more than just 2 proteins. And in face-to-face interaction, you have interaction between more than 2 individuals. In meetings, this is a real data of people moving in an exhibition context, so the proximity of the people in a museum. And also collaboration networks, from science collaboration networks to movie act collaboration network. You can have team of more than 2 individuals. So there is a lot of interest in the topic. So we have, for instance, a recent Nature Physics perspective article with a number of active people in the field, which highlight, this global understanding of why higher order interaction are important for complex systems. If you want a more personal point of view, I advertise my recent book by Cambridge University Press. This is a small 100-page roughly book that is for the Cambridge element. And here I use a more pedagogical introduction to the field and highlight some of the most recent results on the topic. So higher order networks, they come in 2 big classes. Hypergraphs that are mostly used by computer scientists, in which you have hyperedge, so interaction between more than 2 nodes. The hypergraph is formed by a set of these hyperedge, so you have interaction between 1 and 2, or an interaction between 1, 3, and 4, and 1, 3, and 5, and you can consider the set of interaction of different number of individuals, and this forms your hypergraph. Mathematicians are somehow more interested in simplices, but from the network perspective, it's just another way of characterizing higher order interaction. So the terminology is that the zero simplex is a node, the one simplex is a ring, the three simplex is a triangle, and a three simplex is a tetrahedra, and so on. So a simplex is a set of dimension D, is a set of D+1 nodes. And then you use these simplices to indicate the interaction between these nodes, like an hyperedge. And but with simplification, you are allowed to give simplices also a topological and geometrical interpretation, in particular if you put a kind of notion of distance along for the links. A simplex admits as faces the simplex formed by a subset of their nodes. So a tetrahedra, a three simplex, admits as face for node 6 links and 3 triangle. And so the big difference between simplicial complex and hypergraph is that simplicial complex are such that if a triangle is, for instance, then also all is the only difference between simplicial complex and hypergraph. And it is a cost, that you need to include all these phases of the higher dimension simplex in your simplicial complex, but this comes with a big benefit that you can use applied topology and applied geometry to study this structure. So how do you go from a network to a simplicial complex and vice versa? So if you have a simplicial complex, you have a network with interaction, triangle, tetrahedra, and so on. You can go a simplicial complex with this higher order interaction. You can go to a network by performing an operation which is called network skeleton, and just you consider just only the node and the links, and you forget about the higher order interaction. This is the net skeleton of a simplicial complex. And you can do the opposite operation to go from a network to the simplicial complex by doing the clique complex. So every clique, every full connected graph, every triangle formed by 3 links becomes simplex, in which you have this 3-body interaction, and every interaction between 4 nodes, pairwise interaction between 4 nodes becomes a tetrahedra. Now, if you concatenate this operation, you don't go back to the starting point. So this is something important. So you start from a simplicial complex, you do the network skeleton, and then you do the complex. You are not getting, in general, the simplicial complex you are starting from, simply because you are getting something that is as more higher order interaction that was started from. So an important question in inference is, given a network, establish which cliques are actually encoding an higher order interaction, right? So the clique complex might overestimate this number, okay? So you look at higher order network structure, I like to see this in this way, so that really higher order structure includes combinatorial and statistical properties, but also importantly network geometry and network topology properties that are quite important, and they are practically much less important if you just look at the network, while when you look at the simplicial complex, they become really quite important. So let me just mention some important statistical properties of simplicial complexes. So we know that in network, the degree is important. Degree is the number of links a node has. So in a higher order network, you might be interested in the generalized degree. So the generalized degree, for instance, 2, 0, is the number of triangle incident to a node alpha. So you are looking for the number of d-dimensional, two-dimensional simplex, so triangles, incident to a zero-dimensional simplex, so a node, and the specific name of the node is alpha. So you have K20 will be the number of triangle incident to the link alpha. So you can really, given a simplicial complex, you can look at the node, right? For instance, node 3, and you say, well, node 3 is incident to 4 triangle, right? So you can associate a generalized degree to the node 3, but you can also associate a generalized degree to a link. So you can say the link 1, 3 is now incident to 3 triangle. So this will be the generalized degree of the link. And this extend to higher order the of degree that you have in graph. Simplicial complex can be pure, and pure simplicial complex are a good simplification. So they are just formed by a d-dimensional simplex. So for instance, in this picture is only formed by triangle. And in this case, these objects, they can be treated with a tensor, so tensor of d+1 indices. So if the dimension is 2, you have 3 indices, telling you if the triangle R, S, and P is in the simplicial complex or not. So if it is in the simplicial complex, the tensor is 1, if it's not, it's 0. So in terms of adjacency tensor, the generalized degree of the node is the sum of this entry of the tensor when you sum over all the indices that you sum over all the simplices that are incident to the simplex alpha. And actually the interesting combinatorial property between this generalized degree of different dimensions, so you can, they are not only all interdependent. So this is an important combinatorial property, and when you are interested in combinatorial property, of course, you might also be interested in modeling simplicial complexes. And actually, we have been working a lot in modeling with simplicial complexes and higher order network. So the model we came with is this triadic closure model, which is a mechanism which is quite popular in social science and relates to the property of social network to close triangle. So it's very usual that you are a friend of a friend of a friend, right? So you close a triangle. So in order to mimic that, there's been a lot of study about this triadic closure model, and one variation is that you have a new node that arrives in the network, for instance, a new collaboration network. You have a new student that establish a connection with a random node, random scientist, and then establish a second connection with probability P with a neighbor, with a collaborator of his advisor, let's say, and then it closes a triangle. And with probability 1 minus P, he establish a connection that is random. This model has been studied a lot, but here we saw that actually this model that is just combinatorial, just probabilistic, then and local, then generates community, emergent community. So by this microscopic dynamics of closing triangles, you generate community, and I will show you this before. And then you have other models. So you, for instance, you can have a node that enters the simplicial complex, attach 3 triangles to rings. You have a model in which you have at that time you attach a triangle to a random link, and with probability 1 and with probability less than 1, you can kind of close this pi. So you close the 2 adjacent link. And so, as I discussed before, this model generates community, and this model generates emergent geometry. And this is the kind of network that results. So for triadic closure, you see this starting of this kind of community that are forming and disentangling and things like that. And for this other combinatorial model of attachment probability, you see you can form a manifold. So this is interesting phenomena that occurs due to higher order interaction or topological moves. And we have also worked on other framework. So this framework is a framework of growing simplicial complexes, which generates this manifold, growing manifold that are hyperbolic, actually. And another framework in any dimension. So this is in dimension 2, but you can do in dimension 3, 4 arbitrary dimension, and we have the code in my GitHub page. Or you can have a model in which is more like a configuration model, which, the configuration model for a network is a network with a model that generates any network with a given degree distribution. So, and you can have a model in which you fix the generalized degree distribution. So what is the most random model in which you fix the distribution of the generalized degree of the node. So how many triangles are incident to a node. So from more optical complex, we can also have model of hypergraph. So in this way, we can just create in one layer a network, in another layer a structure formed just by triangles, and another layer on tetrahedra, and then you combine the one with another one, and then you have an hypergraph in which you have interaction, which can be pairwise or with 3 individual or more than that. And so just by combining model which have a fixed number order of interaction, you can have multiplex hypergraph. So these are just a kind of highlights of the combinatorial and modeling structure of simplicial complex and hypergraph. Let me just mention topology, which is quite important. So topology is characterize the shape of structure. So you have some invariant topological invariants that are invariant if you stretch or deform the structure are the Betti number. So if you have a circle, the Betti number 0 is the number of connected components, how many connected components are there. If you have Betti 1 is the number of one-dimensional cavity, for instance, the circle has a Betti number 1. The Betti number 2 is a two-dimensional cavity, so a sphere that is empty inside, right, as a two-dimensional cavity, and the torus as this other Betti number, so both Betti 2 and Betti 1. And of course, if you want to characterize network, you realize, of course, this is geometrical structure, but you realize that the statistics of this cavity is quite important. And for example, for this, this is a fungus network. It's not a simplicial complex, so you are not already deciding still which are the field simplices or field faces, but it's clear that here there is a statistic of big cavity that is important to characterize this structure. One thing that we have done is that we have used topology to characterize locally the network structure. So there has been a lot of discussion in the last 20 years about the clustering coefficient, which describe how dense is a neighborhood of a node. And here we characterize this for each node, the node neighborhood. So we consider the node connected to it and their interaction. And then we forgot about the central node. We remove it, and we have a network. And of this network, we do the clique complex. So we fill all the triangles, all the tetrahedra, and so on. And this network, which is this simplicial complex, has the number of nodes equal to the degree of the original node in the middle. And the density of link is equal to the local clustering coefficient Sigma. So if you sample this node neighborhood, right, you have a sample of network with different number of nodes and different density of links. And to respond to the degree and the clustering coefficient of the central node. But now also, if you keep n and rho in the same range, so very comparable to each other, you see that the data set might behave very differently, that some neighborhoods are many connected components, some are much more dense. So the battery number changed, and this is kind of network neighborhood that goes beyond the clustering coefficient that has been quite used in the literature, and this is using topology. So for instance, if you have one node, right, is very different if this node connects regions that are far apart or connect regions that are connected to each other. So always regarding science, what we did is we consider the M community. So the M community is the community formed by M-dimensional simplices connected through M+1 or M-1 dimensional simplices. So you start from triangle, and you go from triangle through links, right? And if there is a river, right, and that link is broken, then you cannot go there. But yes, so here you go from triangle to link. So you have the yellow component and the cyan component, and here you have other community. And these are reflected by the property, spectral property of an operator that is called the higher order Laplacian, which has the eigenvector localized on these communities, either to the links or the triangle of this community. And actually, with this higher order community, we can try to solve some inference problem. And the actual inference problem is, given a network and likely the existence of higher interaction, how do you infer which are the right higher order interaction there? And what we did is we use Zachary-Krateklev network, which is a network in which there is a partition between two groups that is well known, because this data set has been studied by sociologists, was a data set of just one karate master, and then it's split into two parts during the study. So it is known which people choose to go with the old master, which people choose to go to the new master. So given this community structure, we can consider the community induced by higher order interaction, and we can try to match the best match of the higher order community with the correct community as a function of which triangle are actually higher order interaction, which triangle are filled. And then you determine that, for instance, there is here likely a triangle that is not filled, that is not a higher order positive interaction, at least. So So this kind of overview of the structure of higher order networks. But what I'm also interested in the interaction between the structure and the dynamics. And of course, there is an important role of the combinatorial and statistical property, but also the importance of network geometry and topology. So let me just mention this first direction. So with this multiplex hypergraph, actually one can see that using some techniques that are using in multiplex, that you can have cooperative, and when you have cooperative phenomena, percolation problems or spreading problems can become discontinuous. So for instance, you can have one hyperedge that allows the spread of a behavior if all the nodes in the hyperedge are connected, and then it allows the spread to the neighbor nodes. So typically in percolation, you just need one node to be active to spread the interaction, but sometimes for instance, social behavior, you need many individuals to adopt a behavior to be able, for the behavior to be able to be spread. And then you can have this collective phenomena, or you can have other type of collective phenomena, which all leads to continuous transition. So the fact is that in order to spread behavior, you need at least a certain number of node or edge to be infected. And also, we have recently worked with a group in Canada and US, not focusing on social contagion, but also on contagion of biological vectors. And so this paper is published in PRL. And one thing that we have seen in COVID is that super spreading events are super heterogeneous, meaning that is a wide distribution of the size of the people infected, the duration of the event, and the attack rate, so the success spreading of the infection. And so what we want is to interpret in some sense this result with higher order networks. And the idea is that actually when you have infectious disease, infection occurs in location. So you have an individual that can have a different duration of exposure of different location. So it can attack different location for different exposure time. And one is that at the given location, this individual gets infected with a probability theta that is a function of the fraction of infected individual in this location, right? This interaction in a given location be a many-body interaction, actually, because it's between an individual and the individual there. So in order to take into account this evidence of the heterogeneous of superspreading, we consider of a vastly duration of exposure. So there is evidence that human activity is also often vastly, so that so we assume that the exposures to different locations can take a time that is broadly distributed. And then an important element of the model is that there is epidemiological evidence that a minimal infected dose K might be required for an individual to likely be infected. And if you combine these two properties, so burst exposure and minimal dose, you see that the probability of infection theta might be non-linear with the density of infected individual in that location. So you can have even super linear growth of this probability with the probability of the fraction of infected individual, leading to a non-exponential growth and an hysteresis of the phase diagram. And in some cases, this non-exponential growth has been observed. And I mean, although this is theoretical, we hope that this can be, in a sense, verified with data. So higher order networks and dynamics are interacting with this combinatorial property. So you can have combinatorial property in the rule that affects the spreading, for instance, if you need a collective phenomena, or you can have this temporal dimension of and this threshold rule that affects the interaction. But there is also geometry and topology which affect dynamics. And what I will mention here is particular this direction of our higher order network affect and simplicial topology affect dynamics. So when you have a simpler complex and you put a dynamics on it, of course, you are tempted to put a dynamical variable on the nodes, and this is what is typically done on a network, but actually a dynamical variable can live also on the links, like a flux, or actually can also live on a triangle or on a tetrahedra. So you have topological signal, what is called topological signal. So the dynamical variable associated to simplices. So you can have, for instance, citation in a collaboration network that is associated to a given team. You know, 3 individuals, they wrote a series of papers together and collectively they got so many citations, right? Or you can have flux in biological transportation network that is associated. You can have synaptic signals in neurons, or also now it's quite fashionable to study edge signal in the brain after a work by Olaf Spons. And all these are co-chains, so variable associated to simplices, but you have also vector fields like speed wind in the ocean at a given location in the 2-dimensional grid of the ocean, or current at a given rotation. So these are vector, right? But then if you have a tessellation of your ocean with, I don't know, some places where the signal is taken, then you can project the signal on the links of this tessellation, right? So you can treat it always as a co-chain. So we are interested in treating these topological signals because they're being kind of neglected until now. So one thing is that we look at is the Kuramoto model. So the Kuramoto model usually studies the synchronization phenomena of signal associated to a node. So you have a phase associated to a node that can also, that if left alone, oscillates with its own frequency. Each node, and then you have the network, and the network establishes some connection between the node. And so if you allow that neighbor node to tend to align their phases with the phases of the neighbor node, then you phase transition, this coupling constant is large enough. So this is the intrinsic frequency, this is the coupling constant, and this is the tendency of aligning the phases. So if sigma is large enough, then you have a phase transition with an order parameter and a collective phenomenon. that so the phases tries to synchronize at the same time. So the question is how to define the higher order Kuramoto model if the signal is on the links or on the triangle. So in order to do that, yeah, I don't know if I will have time, but let's hope that I will have.
Yeah, there's plenty of time.
So I need to introduce a little bit topology. Okay, I need to introduce a little bit of topology. So we mentioned that we have a simplex is a set of n+1 node now in this notation. So you have this simplex in applied topology and algebraic topology have also an orientation. So the orientation is not a direction, it's just an arbitrary orientation, and typically you have an orientation between the orientation is positive, going between, for instance, a node with smaller label to node with largest label. So from 1 to 2, the orientation is positive in this direction, and from 1 to 2, and then from 2 to 3, and 1 to 3 is positive in this direction. So, and an orientation of J is equal to minus the orientation Ji. So you consider the one chain. One chain is a combination of simplices with coefficient in a given field. For instance, a real. So you can put a real field. Here you have 1, 3 minus 2, 3 plus 2, 4, and this one chain corresponds to this topological part. So you go from 1 to 3, then from T to 3, but inverted with the inverted sign, and then from 4. So there's a mapping between this algebraic element and the topology. So one important operator in algebraic topology is the boundary operator, which map n chain and map one chain. You have for each simplex, you have the boundary operator acts in this way, and this reduced to this fact: if you have a link, the boundary B1 is 2 minus 1, so it's the difference between the two nodes. If you have a triangle, right, the boundary of the triangle will be 1, 2, 2, 3 minus 3, 1. So it's actually exactly the link at the boundary of the triangle. You have this name. And an important property of this boundary operator is that the boundary of the boundary is null. So if you have a triangle, right, the boundary is the 3 links, 1, 2, 2, 3, and minus 3, 1. But then do the boundary of that, this is a closed object, so there is no boundary of that. The boundary is null. So you can do that also algebraically, and you find that this is 0. And this is valid in any dimension. So you may care about this boundary operator, but this can be oriented just in a matrix. And you put your links here and your node here, and the boundary of the link 1, 2 is minus 1 plus 1, minus 1 plus 2, and so on. So you can treat this boundary operator as matrices once you have an order of the links, an order at the basis of the node, and so on. So, of course, this matrix, if you multiply them together, Bn plus 1 is 0, and Bn transpose n plus 1 transpose Bn transpose is 0, because the boundary of the boundary is 0. Okay, so what do you do with this boundary operator? You just work with them. And if you have this combination, B1 transpose, this is the graph Laplacian that is very important to describe diffusion on a network. And here is clear that is positive semi-definite because it is this for this expression. You can also higher order Laplacian, and this is what we mentioned briefly before, in which you can have practically, you can go from n simplices to n-1 simplices, and from n-1 simplices to n simplex again, or you can go from n+1 simplices, from n simplices to n+1 simplices, and then back again. So this higher order Laplacian describe diffusion from n simplices to n simplices going either one dimension up or one dimension down. And it can be decomposed in n down and ln up. And the kernel of this Laplacian is the Betti number n. So an important property is the Hodge decomposition of this Laplacian. So the eigenvector either a eigenvector of a non-zero eigenvalue of the L1 up or L1 down or an harmonic component. And this corresponds to solenoidal component, which is called free, harmonic component or gradient of the signal. So let's use this to define the higher order Kuramoto model on simplicial complex, and this is the paper PRL of 2020. So we are interested in these topological signals, for instance, associated to the links. And what we notice is that the Kuramoto model can be written in terms of the boundary operator, just like this, where theta now is associated to the node, omega is the frequency of the node, and you have a coupling constant, and then this sine function is taken element-wise. So you can work it out, is exactly equal to the expression that is more common to study. So once you have you consider this Kuramoto equation, it's clear that in higher order, for higher order topological signals, so for signals that are defined, for instance, on links or triangles and so on, what you should do, use the higher order boundary equation. And then you have these equations, which you have the phases associated to the link have their own frequency, and then they couple the phase of other link, for instance, through triangle or through node, right? With this coupling constant. So these are higher order interaction. So if you just play with the simplicial complex, you can see that in the sine function you have three-body combination, or two-body if they're mediated by a link is two-body, if they're mediated by a triangle is three-body, and you have a interesting convention of sign that is purely dictated by topology, by this boundary operator. And so this is a intrinsic topological, but also higher order interaction. And a question is, once you have this function on the links, what is the dynamics projected on the triangle or on the nodes, right? What is the dynamics that is projected there? So what you do is discrete curl or the discrete divergence of the signals, but this generalized to any dimension. And what you do is that these two dynamics decouple into a dynamics that synchronization dynamics of the dynamics node or on the projected dynamics of triangle. And these two part of the signal, the solenoidal and the connected to the solenoidal and irrotational part of the signal, synchronize at zero coupling. So you have immediate synchronization of the system as soon as there is some coupling. But if you look at the signal associated to the link exclusively, you would find nothing. And you will find nothing because you have these two parts, the solidonial and the rotational, which synchronize at different frequency, right? They are completely coupled. So if you mix two, you see nothing. And you can also have, reveal this synchronization by filtering the signals on the links. Instead of projecting on the node and on the triangle, you can filter with ln up or ln down. That's essential, because if you don't do that, you don't see anything. So really, you need to perform the correct topological filtering. This is like a Fourier filtering of the signal in order to reveal this collective phenomenon. What you can do also is we said that the projected dynamic was coupled, and then you can couple with the order parameter of the other dynamics. So here is the link interacting with the links through n+1 through the triangle, and you multiply the coupling constant with the order parameter of the project dynamics on the node, and you do a vertical for other. And when you do that, the projected dynamics is not anymore completely decoupled, because the projected dynamic on the triangles depends on the order parameter of the node, and the node depends on the order parameter of the triangle. You do that, the transition becomes explosive and discontinuous. So this we have done on the configuration model of NGF, but we have done also on the network geometry with flavor we find, and also on connectome, and we find always this evidence for this discontinuous transition when there is this adaptive coupling. Finally, mention briefly this. I want to have not only links synchronizing with themselves, but also links synchronizing with the node. Then you can practically have an adaptive concept on the dynamics on the link. You have dynamics on the links with adaptive coupling depending on the projection of the links on the nodes and the projection of the links on the triangle, and you get this continuous transition for signal on the node, for the solidonial signal on the links, and for the irrotational signals for the links simultaneously. So this model is actually amenable to theoretical calculation, and this is the solid line is the comparison with the theory and the simulation. So we have a clear hysteresis loop of this discontinuity transition, and then we studied in particular in the fully connected case. So here there is practically it's not visible, but there is a theoretical line here at top. This continuous transition, the backward one is fully captured by the theory, but the forward one is not captured by the theory, because the theory predicts here that the unstable branch doesn't touch the axis ever for any coupling. And so we have that this forward, this continuous transition is just depending on the network size. So this is just a finite effect, infinite network. So I reach my conclusion. Higher order interaction are ubiquitous in complex systems, and they have rich combinatorial, topological, and geometrical property. And in particular, when you study dynamics, the combinatorial property revealed themselves quite significant when you include contagion dynamics with this bursty exposure time and yes, and collocation and threshold mechanism. And then I mentioned to you this higher order Kuramoto model, which is a general model to capture synchronization of topological signals. Okay, so thank you so much for your attention. This is collaborators of the work that I mentioned are either now in my lab, have been in my lab, and external collaborators.
Okay, thank you, Ginestra, for this talk. Is full of panoramics and complete for the audience. Thank you so much. So now, if you have questions, you can open the microphone. I don't know if someone alguien que quiera participar preguntando o en el chat o directamente. No somos muchos, ¿no? Bueno, okay, I'm going to ask you a question in order to start this. Actually, in terms of the dynamics of a network, suppose that you establish some kind of topology for instance, suppose that about a pandemic, that we are talking about a pandemic, and you can locate the network over a region, for instance, a country. And you have data that dictates the dynamics in some nodes. Right? So what about it? How do you link those data, for instance, the number of infected people in one city with respect to the other, assuming that you have information on how the people move between cities? How do you try to model that kind of interaction and try to explain the data that you can see in the real life? Because actually the only thing that we can see in the pandemics are those numbers, but not exactly the links. How do you try to model those data between, for instance, two cities?
Yeah, so I think there are, I think in topology, there has been some work on modeling and on modeling epidemics on a small world network, trying to see how one can reveal the circle, right? So that there is an underlying circle about that. But yeah, most of the study about this kind of similar question, they are not based on topology typically. They are yeah, based on meta-population data and mobility data. Some good work by Jesus Gomez. I think he worked actually with some data for Colombia. Yeah, so this is yeah, it's of course an interesting, and of course many of the modeling framework, for instance, big modeling frameworks that are used by different states use this mobility information to inform the government. So, this is very important. Yeah.
Okay. And the other question should be about the Kuramoto's model. I know that the transitions between states in the nodes, for instance, is dictated by the shape of the structure of the equations, right? I mean, it's not just the structure of the topology of the network, as well as the dynamics that is imposed by the Kuramoto's model. There should be some kind of way to identify the dynamics. For instance, Kuramoto's model pretends to be one of the universals way to explain, for example, interactions between complex systems. I mean, many interactions, many subjects or nodes participated in the interaction. But suppose that you have a network, well-established network, the topology is fixed, but you can access to measure in some nodes. So Kuramoto's models, it's kind of a way to initiate the research on this kind of inversion of how to figure out what is the real dynamics of a complex network? Or do you think that the Kuramoto's model could be the how to say, it's the most simple or the most complex, I don't know, way to explain the dynamics between a complex network? I mean, the dynamics of the network. Or there are more models that you can impose on the network, and particularly thinking in terms of dynamical systems or coupled differential equations. There are more about the Kuramoto's model for.
So there is, in terms of synchronization, there is not only the Kuramoto model, there is also the coupled oscillator. So you can have, for instance, a dynamics on any node that is already chaotic or whatever. Not just the phase that oscillates, but dynamics itself that is non-trivial on the node, right? And then you can couple this dynamics on the node that is non-trivial with the neighbor one. And you do this through Laplace. So in a graph network, is done through. So it's not that the Kuramoto model is unique for getting synchronization. You can have also at least this major alternative.
Sure.
The phenomena are not always the same. So for instance, the coupled oscillator depends very much on the spectrum of the Laplacian, and in particular the ratio between the largest and the non-zero smallest eigenvalue. While the Kuramoto model is not really sensible for this ratio. So yes, so there are some particular distinction to be made, but yes, the difference between this coupled oscillator and the Kuramoto model is also that the coupled oscillator are all identical. So you have a dynamics on each node can be arbitrary, right? Very complex, complicated, chaotic, but it's the same. So with the same parameter for different nodes. So maybe different initial condition, but the same equation dynamics. X dot is equal f of x. Instead, for Kuramoto, you have heterogeneity, right? So for the Kuramoto, each phase has its own frequency. So they are not equivalent one node with another. One is going slowly and the other going fast. So the equation, if I can just so yeah, so let's say this equation, right? You put sigma equal to 0, so you have just phi dot is equal omega, right? But for any phase, you have a different frequency, right? So for any phase, you have a different frequency. Instead, for the coupled oscillator, you have for each phase, you have this for each variable x associated to the node, you have x dot equal f of x, where this function is always the same. So it can be more complex, identical oscillators, all the nodes the same. Instead, in the Kuramoto, they are heterogeneous. And I think they are the easiest heterogeneous case.
Okay.
Yeah, so.
Okay, thank you.
Yeah.
Okay, I don't know, someone else, ¿alguien más tiene alguna pregunta? Questions? No? probably for the students, but maybe they will see watch the video later. What are the opportunities to do graduate studies there where you are a professor, Ginestra?
Okay, so we should do this probably active students are interested. Typically for UK it's very difficult to get a fellowship. PhD fellowship is really challenging, but I think there used to be at least some agreement with Mexico of some fellowship from Mexico, from Mexico or UK, specific one. And if there is such a route, that would facilitate the thing. I think we should, maybe I should get informed, and maybe you can also see if there is agreement or some.
Yeah, actually,
Mexico, UK,
yeah,
connection.
There is some links with the British Council, and actually many people go to US or go to England sometimes, so UK
yes.
with using the British Council facilitates, I think.
Yes. So I think, you know, the standard route is quite complicated, but if there is this kind of agreement, it can be good. So for instance, we have many students from China also, because there is an agreement with China, and there is this China scholarship fellowship. And I think that also with Mexico, there is something.
Yeah,
I never had a student from Mexico, but I think it's an option.
We used to have some scholarships from the government, I mean, to financing PhD students particularly. Now we are in trouble with that because the crisis and the new government, but eventually I think we will recover those scholarships to study abroad. But essentially you have a master's and PhD programs, in this direction of the networking, or it's just a broad program in physics or applied mathematics? How is that?
Yeah, I'm in the mathematics department. Yes, so the master is, we have masters in data analytics or something like that. But during the master, the student don't do research. So and the master is costly, right? It's not that you get a fellowship, but you need to pay for studying. So the master is costly and is not really linked to direct research. It's more about studying.
Okay. Taking classes.
Yeah. So for the PhD, the PhD is a possibility, but it's very challenging. So, for instance, it's 2 years that I don't have a new PhD. So it's very challenging, and so if there are some fellowship or things like that, it's the way to go.
Okay. Well, so I thank you again for the talk, and I appreciate that your availability for this time, and I know that maybe you are around out of the dinner, so okay. Bueno, I want to switch to Spanish. Les quiero agradecer a los presentes, bueno, que hayan participado, y pues esperamos verlos la próxima sesión. So thank you again, Ginestra, and keep in touch, please, and see you again.
Thank you.
Later.
Yeah.
Thank
you. Bye-bye.
Bye.
Bye-bye.